Hi, my name is Gabe Loewinger. I'm a fourth-year PhD student in the Department of Biostatistics here at Harvard School of Public Health. Today, I'm going to be speaking about multi-study machine learning methods for in vivo estimation of dopamine in humans. Dopaminergic pathways like the nigrostriatal or mesolimbic dopamine systems have been implicated in learning, memory, motivation, as well as a number of disease states. And for that reason, there's been ongoing interest in measuring dopamine concentration changes in humans in real time. This was recently enabled with the application of fast-scan cyclic voltammetry to human participants. And this technique is an electrochemical technology that proceeds by varying the voltage potential across an electrode that's implanted deep into the brain of humans and measuring the changes in current that occur. These changes in current can then be mapped to dopamine concentration estimates via a statistical model. The recordings are made by invasively implanting electrodes into the striatum of human participants who are undergoing neurosurgery and then recording these dopamine signals during behavioral tasks in an attempt to correlate brain activity with their performance on these behavioral tasks. One of the challenges, as I mentioned, is that it does not directly estimate, the technique does not directly record dopamine concentration. Rather, it records these electrical signals that have to be mapped to the scientific measure of interest, dopamine concentration, via a statistical model. The way that one typically trains these prediction models is by generating data sets in vitro in solutions of synthetic dopamine where the true concentration is known, and then applying these statistical models to the recordings made in the brain to generate actual concentration estimates in vivo. However, there's considerable heterogeneity between electrodes and their average response profiles, which I've shown here on the right in the figure. And moreover, the response profiles in vitro differ considerably from that in vivo in the brain. So assessing how well these models generalize is really critical to ensure that the scientific conclusions made from in vivo estimates are as accurate as possible. One way to kind of mimic this procedure is to conduct a hold one study out prediction performance. So in other words, take many different electrodes, produce these in vitro calibration data sets in each electrode, train statistical model on some subset of these electrodes, and then assess their performance in a data set not used during training. So what we sought to do here was to improve concentration estimates with multi-study machine learning methods. And multi-study machine learning methods seek to aggregate and borrow information from many different data sets to improve the model generalizability and prediction performance in settings not used in training. So one important challenge is how to account for the fact that there is considerable heterogeneity between the electrodes. So what we sought to do was use integer programming or optimization techniques to try and minimize the distance between the data sets we use for training in terms of the average response profile or the covariates, and the covariates or the average response profile of the electrode that we're trying to make predictions on, whether that be an in vivo electrode or an electrode's calibration data set that we're assessing performance on. So we use this integer optimization program, and the solution to this integer program produces basically a recipe of the number of observations to take from the different training calibration data sets to then create a calibration data set that has an average response profile that matches that of the test set that we're interested in. So we follow this recipe, fit a model, and then we make predictions on the data set that we, on the test data set, and assess how well it predicts. On the left, what we show is that our method, rather a random resampling approach that tries to match these covariates, does quite a bit better than the standard in the field. And that principal component regression substantially outperforms the lasso, which is one of the main approaches used currently in human voltammetry. In the middle panel, I show that the integer program effectively matches and creates creates data sets that have average response profiles that match the target electrode. Finally, on the right, I show that the integer programming approach does better in terms of prediction performance compared to random resampling and substantially improves the runtime of the algorithm. In conclusion, the principal component regression approach outperforms the lasso. Covariate matching with random resampling improves prediction performance, and the integer optimization procedure, importantly, vastly improves speed and prediction performance compared to random resampling. The generalizability of these models clearly benefits greatly from multi-study machine learning methods. I'd like to thank the following people for their contributions to this work: Thanks so much for coming to listen, and please feel free to reach out with any questions. Thanks so much.